in which we are taking 1 mole of our ideal gas, and we're given the initial state and subjected to reversible doubling of its volume, followed by reversible doubling of its volume at constant pressure, then doubling of its pressure at constant volume, and then subsequently they return it back to the initial state along the path P is equal to here. So we get some function of volume. So in our PV space, we've got a path we're following, and we're supposed to calculate the heat and the work during each of these. So we start with N1 is equal to 1 mole, T1 is equal to 273 K. Zoom out. K. P1 is equal to 1 ATM. V1 then is equal to nRT over P is equal to 1 times 8.2 times 10 to the minus 2 times 273 divided by 1 is equal to 22.4 liters. That's our initial state. We got a constant pressure transformation. So that means that P2 is equal to 1 ATM still, and N2 is equal to 1 mole still. And we're told that we're double the volume, which means V2 is equal to 44.8 liters. So now T2 is equal to PV over NR is equal to 1 times 44.8 divided by 1 times 8.2 times 10 to the minus 2 is equal to 546 K. Okay, and we're supposed to find the heat and the work. Well, work is equal to P delta V is equal to 1 ATM times 44.8 minus 22.4 liter times 101 joule per ATML is equal to 2,264 joule. So, and then constant pressure. So we can use the heat capacity at constant pressure. It's equal to Cp n delta T and Cp minus Cv equals R. And we don't have a Cv, so let's Cv equals 3 has R from before. So that means that Cp is equal to 5/2 R. Something about this textbook, Gaskell, in many of his problems, leaves out the heat capacities, but if you look at the ones where he gives it to you, he always uses 3/2 R. So if you find yourself needing a heat capacity, this is a pretty good guess. And I don't know if you want to call this a well-known feature or bug in the text. It is what it is. So, okay, here we are, which means that now, substituting this into here, we get QP is equal to 5/2 times 8.314 times 546 minus 273 times 1 mole. QP is equal to 5674 joule. Okay, that's the first problem. And this is page 6. So then the next problem is to take this state and to transform constant V to double its pressure, which means that now N3 still 1 mole, T3, P3 doubles its pressure, so this is now 2 atm, and its constant volume, so V3 is still equal to 44.8 liter. Okay, and doing this, T is equal to PV over NR is equal to 2 times 44.8 divided by 1 times 8.2 times 10 to the minus 2. Temperature is now 1093 K. So we've got the new state. And for this constant volume, W is equal to P delta V is equal to 0 joule. And QV is equal to CVN delta T. Remember, at delta U is equal to Q minus W at 0, and the change in internal energy is given by this heat capacity relationship. So that gives us 3/2 times 8.314, the gas constant, times 1 times 1093 minus 546. QV is equal to 6821 joule. Okay. And then the next step is to transform this back to state 1 along a path. So I'm just going to rewrite this. N3, T3, P3, P3 is equal to 1 mole 1093 K 2 ATM V 44.8 goes back to N1 1 mole 273 K P1 is equal to 1 ATM. P1 is equal to 22.4 liter. And we're following the expression P is equal to, what is it? 6.643 times 10 to the minus 4 V squared plus 0.667. Okay. So in this case, work is equal to integral P dV. So before we were using basically delta W here, we're this way. That, right? So the work comes from the integral of P as a function of V, and this is going to be integral of volume from 4.8 to 22.4 times 6.643 times 10 to the minus 4 V squared plus 0.667 dV. And all of that's going to be times 101 joule per ATML. W is equal to minus 3268 joule. And the change in internal energy comes from the heat capacity is equal to 1 times 3/2 times R 8.314 times 273 minus 1093. Delta U is equal to minus 10,226 joule, and delta U is equal to Q minus W, which means U is equal to delta U plus W, it's equal to minus 10,226 plus negative 3268. U is equal to minus 13494 joule. And that's the change in the work done and the change in heat.